All right, everyone. My name is Connor Davis. I was the group leader for Group 1, and we did experiment 3 of the refrigeration cycle. The group reporter is Madeline, and the other members are Bo and Dalton. So just a brief overview of what we're talking about. Giving some background to what is a heat pump, how we measure the coefficient of performance for a heat pump and what it means, and then what the refrigeration cycle looks like. Then we're talking about the process, what the goals of the experiment are, the apparatus we'll be using, and the process we'll go about to perform the experiment. And then just a quick simple calculation on how to calculate the coefficient of performance for a heat pump. All right, just some background. So a heat pump is basically just a device used to heat or cool a space depending on the environment conditions, like summer or winter. It does this by absorbing heat from a lower temperature source and rejecting it to a higher temperature source. And when we go from low temp to a high temp, we'll have some kind of work involved. You can see that here in the diagram. The coefficient of performance for a heat pump basically is a ratio that tells us how efficient our heat pump is. There's going to be a ratio of what we want out from our heat pump, which is a high heat transfer, over what we have to put in, which is going to be work. All right, here's a representation of the refrigeration cycle. This is just a temperature versus specific entropy of this process. And then on the left here, everything you see in the black dashed box is going to be the components that make up a heat pump. Like I said in the previous slide, you have a low temp absorbing heat, projecting it to a high temp, and then there's work involved by compressor. And this refrigeration cycle, starting with the evaporator. Evaporator is going to take a liquid, add heat to it, convert it to a vapor. It's going to be sent to the compressor, which increase the pressure, send it up to state 1. Condenser is going to take that vapor, condense it down to a liquid. And then our expansion valve is going to decrease the pressure, bring us further down the vapor dome to state 3 here. And here are some other diagrams of the refrigeration cycle. On the left, we have pressure versus specific enthalpy. This is what we will be constructing in the experiment. And then this is just another pressure versus specific volume of the refrigeration cycle. For the pressure versus specific enthalpy, the black lines and dots represent an ideal refrigeration cycle. It's never going to be the case. So the red lines and points are for an actual refrigeration cycle, and that's just due to pressure losses from friction, leaks in our valves, and then our compressor not being totally reversible. So that's what the actual cycle looks like, and will better represent the real world case. All right, so just here the objectives, purpose of doing this experiment is to perform a thermodynamic analysis of a heat pump, learn how to measure coefficient of performance for a heat pump, and then learn how to represent a vapor compression refrigeration cycle on a pressure versus specific enthalpy diagram. This is the apparatus we'll be using. This is a picture of the actual equipment. On the left is the diagram of the cycle. So here we're going to have these 2 water pumps, which will be supplying water to the evaporator and to the condenser, just for them to be able to perform that heat exchange. And here the orange cycle is the actual refrigeration cycle. Our working fluid would be R134A. And the same cycle with the evaporator on the right, condenser on the, compressor on the top, condenser on the left, and then this AVEX valve is just our thermostatic expansion valve, which again is going to decrease that pressure while maintaining constant enthalpy, and then it'll be sent right back to the evaporator, and the process will repeat. All right, so this experiment is broken up into 2 parts. So the first part will be finding the coefficient of performance for our heat pump. We're using CRCVC software, turning on devices, adjusting different settings, setting the flow rates, and then once the system stabilizes, we'll be measuring different values in order to calculate the coefficient performance. The second part of the experiment is constructing the pressure versus specific enthalpy diagram. It's pretty much the same process as exercise 1, except here we'll be adjusting the flow rate on the evaporator heat exchanger, and then we'll be taking pressure and temperature readings at different points in our cycle. All right, so to be able to measure the coefficient of performance and to document or draw the pressure versus specific enthalpy diagram, we're going to need the power of the compressor, water flow rates, again, temperature and pressure readings at different points in our cycle, and then we're using the R134A tables to find the enthalpy from the pressure temperature readings to plot the refrigeration cycle. This is the equation we'll be using to calculate the coefficient of performance. This is for the real case. There's another equation for the ideal case. And then some assumptions we'll be making is that the enthalpy is going to be the same at the expansion valve inlet and exit. There'll be no pressure drop on our condenser. This isn't entirely true, but just simplifies the problem a little bit. And then entropy is also the same at the compressor inlet and exit as well. So here's just a sample calculation for the coefficient performance. Use this equation you see here on the left. The mass flow rate came from the lab manual. That's the specific heat for water. And then I just gave a guesstimate on what I thought the change in temperature might be, and then what the work at the compressor might be. Put all that into the equation, and I got about 3.1. Basically just a ratio says that 3.1 joules of heat transfer per 1 joule of work input. So. And there are my references. Any questions?